Hey, hackers, how are you today? Hello, everyone. Hello, Maroki, how are you? And Dina, hi. Thank you so much for joining. And I'm really excited for our workshop today. Doing great. Um, Hello, hat. I know, today I have a special hat on, just, just, just for fun, just to liven things up a little bit. It's your first live session? That's awesome. I'm so glad that you're here to join. And yeah, today's session, it's going to be a bit shorter than normal. We're going to have a 1 hour session instead of 2 hours. But we're going to still cover a lot of content. We're going to cover two different machine learning algorithms today. And so I wanted to post in the chat the link here in case you are unable to get that. Yeah, this is the link to check in, and we really appreciate you checking in because it helps us understand um, what kinds of content you all are interested in and how we can do better in the future. Hi there, Asmam. How are you? Great to see you again from yesterday's stream. I see a lot of familiar faces, friendly faces from yesterday's stream. And yeah, so why don't we just go ahead and get started? I want to show my screen and show you the image that I showed from yesterday. All right, everyone, just give me 1 second. Oh, now I see why. Okay, so here's the image from yesterday. And I think I remember, here's the link. I think I remember going through this a little bit with all of you. But before we do that, actually, Prabhat Kumar says, hey, Stephen, what did we cover in the previous session? I missed the previous one. And in fact, if any of you missed the previous session, I'm happy to send you a link to that information. Here it is. That link will send you to lesson number 1, which was what we did yesterday. And today we're going to try and cover lessons 2 and 3, actually. So hopefully you can check that out. But yeah, I mean, this lesson is based on random forest, which we talked about a little bit as an ensemble of decision trees. And in fact, we have a decision tree right here. This data set is taken from Kaggle, and it is a data set of kyphosis. So kyphosis is a disease of the spine. And it's when someone's spine becomes a little bit misaligned. Um, and so, yeah, let me show you. There's this diagram of a kyphosis patient. Let's see. Yeah, so I think basically kyphosis, I'm not listen, I don't really know much about medicine. I'm just a programmer, but based on what I've read, kyphosis is sort of when your spine curves too much in your upper spine, so up in the top. And so that is sort of the idea. And we're going to use this this decision tree to predict kyphosis. So the start variable, I didn't tell you this at the time, but the start variable has to do with where the curvature starts on the spinal cord. So you saw that image I just showed of the seventh vertebrae, but you know, start could be at the eighth vertebrae or at the 14th vertebrae. And so the start is representing which vertebra is the bending beginning. And the age is a metric related to the patient's age. And so you could have 4.6, 9.2, things of that nature. Okay, and you know, if you download this data into your computer, which you can do, you'll want to download the kyphosis.csv file. You'll want to download this lesson 2 blank if you want to follow along a little bit today. All right, and let me open up my code editor so that you all can see this. And I'll do a little review of what we did yesterday as well. Here's my screen, by the way, in case you can't see that. I don't know if you all were here for our k-means clustering example yesterday. But in that example, we learned how to classify data by clustering it into different groups. And so we had our bullseye example yesterday. We also looked at our eruptions from the Old Faithful geyser. And Darshini says, am I late? Nope, we only just started a little bit ago. We talked a little bit about the problem we're going to work on first today. Right? So now we're going to be having a new lesson here. I'm going to call this lesson 2.801. Today is the first day of August where I am, so pretty cool stuff. But yeah, I'm going to copy and paste all these libraries that we use into my file. And you can get these from the GitHub notebook, the one on GitHub. But yeah, these first three we actually imported last time for our k-means clustering example. But these new ones, these sklearn modules, these are different actually than the k-means module. So the first one is this train test split method, and that is going to be for supervised learning. So let's write a comment here. This is for supervised learning. And we talked about that a little bit in our presentation yesterday when we were talking about the differences between supervised and unsupervised learning. And you might remember that unsupervised learning is similar to our clustering algorithm, where we don't have any kind of categorization going on. And supervised learning is where we are, we don't have any kind of tagging, human tagging. And supervised learning is where a human goes in and tags the answers ahead of time in the data set. Okay, and so we have our, this is our random forest. classifier and our decision tree. And so we're going to import both of those algorithms today. And these are some metrics to evaluate our models. So we're going to talk about confusion matrix, accuracy score, things like this today as well. So let's run this on our base environment. Your base environment should be enough. It should have all of these things imported. If you have Conda or some other development environment. Yeah, I'm glad you thought that was an interesting example, Bugbreaker. I'm glad you enjoy it. So anyway, here we are. I'm actually thinking maybe is this gonna help it be a little bigger on your screen? I think so. Yeah, maybe that you can see this a little bit better now. But let's read in some data from our kyphosis data set. And remember, I just dropped this number axis because it's just an index, but you don't have to do that part. But yeah, remember to use this read CSV method, which is going to actually load the data in from your comma separated values file. You can see we have these variables here to the age and the start vertebra, and then the kyphosis itself, absent or present. It says so in the data set. So, this is different than our k-means clustering example because the data is already coming out pre-labeled. Right? And if anyone's curious about this, where to get this data set in its original form, this is the original source on Kaggle. And you can see some people have some really interesting applications where they predict the kyphosis with different algorithms that are not just random forest. But you'll see that we're going to get pretty good accuracy in just using our simple decision tree. Okay. All right, so now we're going to move on and implement the decision tree that we had in our previous example. And I'm actually going to try and I'm going to try and implement this using the code sample. So you all can follow along with the image on the notebook. You can see that online. This is that same tree that we've been looking at in these past few days. And we're going to actually try and implement it using a function. And I'm going to call this function simple tree because it's just one decision tree. And we're going to have two variables, age, start. So, if I were to write a little function definition here, I would say that this function is a decision tree that takes in two features, age and start, or floats. Actually, I think age is an integer. I think they're actually, they are floats. And so then, returns the kyphosis prediction. It's going to be either present or absent Boolean, basically. So it can either be present or absent, this tree. Right? And so the first thing we'll do is say if start is less than 8.5, we want to go into that no branch of the tree. And when we go to the no branch, it gives us a value of 0.58. And so 0.58 was the probability that the patient has kyphosis. And so I'm actually going to have this return a prediction and not just a number like 0.58. I'm going to have it take a random sample from a binomial distribution. It's going to actually choose either 0 or 1 based on a probability of 0.58. Right? I don't know if you've ever seen this type of thing work before. Oh, sorry, I should write P equals. But it will choose either 0 or 1 with a 58% probability. All right? And so that is the way that this binomial distribution works. And so we're actually going to get a Boolean, a present or absent, 0 or 1. All right, so this is the first node of our decision tree. The second node we're going to look at here, if start is greater than or equal to 14, just return 0, because actually the probability, if the vertebra is so far down that it's even more than the 14th vertebra, it's almost certainly not kyphosis. That's actually certainly not kyphosis, so we just return a 0. And then in the third node, we have if age is less than 4.6, return 0. So again, it's almost certainly not kyphosis if the patient is so young. And in this fourth node, this is if everything makes it through the branches and gets to this age greater than or equal to 9.2 node, then if that's satisfied, the patient has a 14% chance of having kyphosis. And if not, then the patient has a 57% chance of developing kyphosis. Right? So we've now accounted for every possibility in our decision tree. If anybody needs to look back at that decision tree, once again, it's available on the GitHub page. I'll post it just at the bottom once more for you. But yeah, now I actually want to implement our decision tree and see if we can make some predictions. So let's make a new variable called kyphosis prediction. And we will say that for data in our data frame, we want a single prediction to be governed by our simple tree algorithm, where the first feature is the first column in the data set, second feature is the second column in the data set, because if you remember, column 1 here is age, and column 2 is start. So that's how we define that. And then the actual value of kyphosis is pre-labeled by the data set. So in other words, a physician or someone who knows about kyphosis went in and actually diagnosed these patients. And so we have the real answer to our problems in the 0 column. And we're going to say that if the 0 column is equal to present, that's a 1. And if not, that's a 0. True, false. So now, if our prediction, so actually let's just look at our predictions now and see what we get. what we need to append. If our prediction equal to the actual, then we will say that we had a successful prediction. And if not, then we will say that the prediction was unsuccessful. And so now we can just take the ratio of our successful predictions to the total number of cases in our data set. Oh, run that cell. Did that yesterday too. But yeah, you can see we get about a 75 to 80% accuracy here, right? But now we're going to implement a random forest method. And so you can see, actually, before we do that, let's see how the accuracy changes every time we hit this button, right? Because you can hit this button a bunch of different times and we get slightly different answers. So make a new column called accuracy scores. This is where I'll just have it, I'll have a loop run this code 100 times. And I'm just gonna put this in a function. So that it returns the accuracy every time. And now when we do this, we can actually plot a histogram of our accuracy scores. We can print the mean results. And the standard deviation. And the reason why we're doing this is because every time we run this model, because it's kind of a random model in a certain sense, the accuracy will change. If you think about this random distribution here, random binomial, sometimes this guess might get lucky, and sometimes it might get unlucky. So on this side of the distribution, a lot of guesses were unlucky. On the right-hand side of the distribution, a lot of the guesses were really lucky. But if you average all of these out, you get an average accuracy of around 78%. Okay. And a few folks have asked for part 1. So let me send that one more time, just so that everybody has that. So there's the link to part 1. You can see the files and the data that we used. Oh, yes, sorry about that. Thank you. No problem. Oh, the recording link, that should be on Twitch. So you can get that on Twitch. Just look for Using ML Algorithms and Data Part 1. And it should be there. But yeah, so this is the idea with our decision tree. But now we're going to move on to random forest. And so let me show you using Wikipedia. Well, yeah, I think I'm actually going to show you using Wikipedia because they have a really good diagram. Okay, and so Bugrigger says, every time the normal distribution varies. Is that why the accuracy is varying? It's because the binomial distribution is random. So we're using random variables in our data set. And so to be honest, your accuracy is not really something that is super fixed because it can change with the adjusting of your parameters. And it can also change with the division of your train and test split, as we will see. So in machine learning, a lot of the times the accuracy of your model is not 100% fixed. It can change. But that's a really good observation. So let's check out this diagram here. I'll zoom in, I guess. Yeah. So imagine that instead of dealing with one simple tree like we did in this case, oh, great, I'm glad you found that on Twitch. Hi. And so instead of dealing with just one simple tree, the random forest distribution is dealing with an ensemble of trees. So that means that you don't just have one tree, you have n different trees. And they're each built a slightly different way with slightly different threshold values at each tree. That's right, Prajwal. Random forest is a combination of decision trees. And then all of these decision trees will take a vote on the answer. So this decision tree 1 will write whether it thinks that there's kyphosis. Decision tree 2 will write whether it thinks there's kyphosis, and so on. And if most of the decision trees think that there's kyphosis, then the final class of the data will be kyphosis. Okay. So let's go ahead and actually check that out. And we can really do this. All right. So we can really do this with the sklearn package. So I'm going to create a new variable called x, and this is going to be where we store our features. So we don't want to have the kyphosis data column in this feature list. But then I'll have a second variable, which will be representing the tags given by the human tags of the kyphosis diagnosis. This is what we're sort of trying to train towards. And so now we're going to split this data into train test data sets. And we do so randomly, okay? So that's why there's a little bit of variation from time to time on exactly what you will get here. But we're going to say x train, x test, so the features, train test, y train, and y test. So these are the tags for train and test data sets. Okay. And so we use our module that we imported from before, train test split, xy. And when we do that, you can see that we'll get this data that is train data. So column number 65, 55, 14, 17. And then we'll also get our tests. Now notice none of these are the same as the train. 42, 69, 3. It's a much smaller data set. So we're going to use this first x train as our features for calibrating the model, and then our test to validate it. Okay. So let's have a random forest classifier object. We're going to fit that with our train data. Okay. And now afterwards, we're going to do is take a score. And are we going to score based on the train data? No, we're actually going to score based on the test data. So we use the test data to evaluate the accuracy of the model. If we use the trained data to evaluate the accuracy of the model, we're always going to get a really high accuracy, right? Because the model has been perfectly optimized to get the best score possible on trained data. And yeah, that would be what we call an overfit, as Buckbreaker said. So we want to actually evaluate the model based on their test data. Right? So when we run this code, we get a higher score. And this is higher than any of our decision tree. We ran our decision tree 100 times, and it never reached 85%. But now our random forest model is reaching almost 86%. So you can clearly see that the random forest with our ensemble of decision trees is substantially better than the simple decision tree model. Right? So does anybody have any questions about this? I think actually we're going to move on to the Markov decision process because we're a little bit short on time, like I said, unfortunately today. I have to keep it a bit shorter. Okay, well, if you have a question, please don't hesitate, don't hesitate to reach out. Love getting questions about these kinds of things, and it would be great to hear from you and answer any questions you might have about the random forest method. But in this final lesson, which we will do in lesson 3, so I'll send the link to that. This final lesson is going to be based on the Markov decision process algorithm. And this one is pretty tough to understand at first. But we're going to get through it. All right, so we do have one question. If we have multiple features in the data, different features could be used as nodes for a single decision tree. That is absolutely correct. So I don't know if you joined for last time when we were focused on the simple decision tree model that we use today. But if you'll notice, in this model, the different features each have a node. So we have 2 different features, not just one. And they're in the same exact simple tree for a decision tree, as different nodes. So you could extend this to have as many different features as you want in your tree. The tree can just grow and grow and grow, and you could limit the size of the tree. But even so, if you have enough trees in your ensemble, each one will try out different features, and maybe some of them will be really good at guessing. Right? And so that's kind of the idea with the decision tree. Exactly, each tree may be unique. That's exactly right. And in fact, that's where the power of the model comes from. Because if all the trees were the same, it wouldn't be any better than a simple decision tree. All right, but today we're going to use our last piece of time to talk a little more about the Markov decision process algorithm. And I want to emphasize again, which we talked about earlier, that the Markov decision process is a reinforcement learning algorithm. So this is semi-supervised algorithm. Someone last session asked, "Hey, I got an interview question about semi-supervised algorithms." Well, this is exactly what it is. And so in this case, the model is asked to design a policy to fit a scenario. And the scenario is it's human input. So this scenario is something that we are designing as the humans in this model. So that's why it's semi-supervised, because we're telling the model what states can you be in, what transitions are allowed, what actions can you take, and what outcomes can those actions have. And yeah, without telling the model this information, it would really not be as effective. But at the same time, we're not telling it what to do either, right? Now, you could think of semi-supervised learning as, yeah, maybe like you're trying to you have a class of kids at school, and you're trying to give them an art project, and you give them certain tools, like maybe you give them a paintbrush, and you tell them, um, you know, if you paint such and such painting, maybe like a landscape painting, then you can go to recess 5 minutes early. But if you paint a portrait, um, then I'll give you a prize, like an eraser or something. We're not telling the students that they should paint one or the other. They kind of have to decide on their own based on the outcomes what's the best thing to do. Right? So now let me give you an example instead of my recess example, which is not really as good as this one. This is a little more concrete. But this is a travel scenario. So these are two cities in California, um, San Francisco and Los Angeles. And actually, I have to travel to San Francisco um, pretty soon. So this is good for me to know. uh, but anyway, from San Francisco to Los Angeles, you could travel by train. And actually, in the US, we have trains that are not super fast compared to some other countries. So it actually takes 11 hours to get from San Francisco to Los Angeles on the train. By car, you can take a highway and arrive in Los Angeles after 6 hours, just 6 hours, which is almost half the time of the train. But then, with the fastest option, of course, if you take a plane, it would take 1.5 hours. So, based on this information, if you wanted to choose the fastest trip, which one would you choose? Well, it's not super difficult to tell from these times. You would want to take the plane, right? Because if it's only going to take 1.5 hours, it's always going to be faster. But let's add some complication here. We're going to add some complication. Now I will say that the car ride takes 10% chance of severe traffic. So if there is severe traffic, it could add up to an hour to your car. Exactly. There are trade-offs, as you said. There are trade-offs. And so we're gonna tell the model about some of those trade-offs. So this is one of those trade-offs. 10% chance of severe traffic. Okay. Look at this. I've made some complicated adjustments to our plane now. 10% chance of a security delay. That takes 2 hours. 25% chance of a plane delay. That takes 3 hours. And a 5% chance of a deplane delay, which means getting off the plane, takes 1 hour. And some of these are more likely than others. I think maybe this is overstating it a little bit. I don't think I've ever been in an airport in the United States that has this issue, or anywhere really. But yeah, this is a little unrealistic, but based just taking these values, right? Let's say we went to the airport and we calculated that this is the real chance of these things happening. Now, all of a sudden, what's the best route to take? Is it still the plane? I'll give you a chance to think about that. So Ash 69X says still the plane. But what would you choose if you needed to get to LA in 8 hours or less? So it's true that the plane is still the best choice because most of the time you will not run into these issues. But let's say that you needed to get to LA in 8 hours. So Ash 69X, you are correct. It is still the plane. But as Osman says, car is the safest. Because if you think about it, if you needed to get to LA in 8 hours or less, let's imagine you get a security delay, 2.5 hours. You get a plane delay, 3 hours. And you get a deplane delay, 1.1 hours. Now, all of a sudden, this is going to take you more than 8 hours. Whereas with the car, even if you hit severe traffic, there's absolutely no chance that you will get there in more than 8 hours, right? If you add all of these up, 2.5 plus 3 is 5.5, plus 1.5 is 7. Then this will bring you all the way to 8.1 hours. Right? So the model is bound to conditions. That's how the feedback is given to it. So exactly. So we can choose different goals. So we can tell the model, let's give you this constraint, and I want you to optimize and find the best pathway given that constraint. So we can say we want as fast as possible, and then it will be still the plane, just like Ash says. We can give a different constraint and say we want it to be 8 hours or less every single time, and then that's the car, right? And this is just how humans do as well. I mean, think about this, right? If I want to get to the place fastest, I'll take this plane. But maybe if I want to get there the cheapest way, I might take the train. Or if I know I have a meeting in Los Angeles, and I must get back for the meeting, I cannot have any delays at all, I might take the car so that I know I will arrive after 8 hours or less. Okay. So in this case, we choose the car. But actually, the Markov decision process has even a different answer. I forgot about this answer, but this is even different. This is an even better choice here. I don't think anybody came up with this. I didn't even come up with this after doing this the first time. But it turns out that the actual optimal solution is to go home after spending 1 hour at the airport. So here's what the Markov decision process algorithm says to do. Go to the airport. Spend 1 hour at the airport. And buy your plane ticket and everything. And if you wait in line for more than 1 hour, immediately jump in your car and drive to Los Angeles. Because you know that if you wait in line for less than 1 hour, then everything else, no matter how many delays you get, you will still arrive at 8 hours or less. right? So this is one of the benefits of Markov decision process, is that the strategy might not be so easy to decide by a human. There may be other strategies that we don't think of that will optimize even better. So this strategy, on average, will get us to LA even faster, but it will still never take more than 8 hours, right? So this is actually the best strategy. Yeah, it's hard for us to think of these unless we have some help with our algorithm. So we can think of all of these different locations as different states. So that we can be in. So first we start off in S0, which is our very first state here in San Francisco. And we can transition into any of these other states. Let's say we transition into S3 or S1 or S6, right? And then we can transition back out of those if we want. We can go from S1 back to S0. But that would incur a penalty, right? Because S0 to S1, we took 6 hours to do that. And we could also choose to go to S2, but then there's a 10% chance of 1 hour traffic in S2 to S3. And so that's sort of how the Markov chain works. Actually, do I need to remember the code for every algorithm, or is it okay if I knew what the specific algorithm does? I think it's okay to just know what the algorithm does, right? Because honestly, I don't know if anybody remembers the code to every algorithm unless they maybe work on that themselves. Yeah, the vertices have penalty weights. Exactly, yes, Mom. And Bugrigger says Dijkstra. I don't know if any of you have heard of this algorithm, but actually let's look at it because it's kind of relevant to today. It's a way to find the shortest path between A and B. And so essentially we're looking for this shortest path, and there are many different complex algorithms to optimize for this shortest path problem. But essentially, this is exactly what we're interested in for today. Okay, so if you're unfamiliar with Dijkstra's algorithm, this is a really interesting problem. We're not really going to cover it today, but yes, it is quite difficult to sort of figure this out. So going back to our example, we will set up our penalties for different transitions in a matrix that we call the state transition matrix. And so this is kind of, we can think about, in our case, the probability of severe traffic if car is chosen. So if you choose car, then the probability that we transition into the traffic state, which is state number 2, you see here, is 0.1, right? But so we then go in our matrix, we go to the first row, row 1, not the 0 row, row 1, and then we go to column number 2, 1, 2, and we fill this value with 0.1. But can anyone tell me what the value of row 1, column 7 would be? I know I don't have it written here. This only goes to 5 columns. But let's imagine, what would P17? This is the probability that state 1 will transition into state 7 directly. So the probability that we land on the severe traffic mode is 10%. But if the probability of severe traffic is 10%, what's the probability that we just go straight from our 6-hour drive? It only takes 6 hours to get to Los Angeles. What's that probability? Is it 10% as well? Is it 0.2? So actually P17 is the remaining probability. So it's actually 0.9. Yeah, as Osman said, 0.9. Because if we have a 10% chance of severe traffic, which means that, okay, our car ride lasts 6 hours, and then maybe we have an extra 10% severe traffic, then there's a 90% chance that we won't have severe traffic. And so we'll go straight to our destination. It's the opposite event. Exactly. It's the not severe traffic event. E minus Q equals 1. Exactly. So that's kind of how this matrix works. And so every single value, every probability will have a transition probability. There are some transitions that you can't make. I mean, think about this, right? If we go from 0 to 3, that's certainly possible. But once we're on the plane and we're in flight, is it possible to transition from state 4 into taking the train on state 6? No, I think we would have to actually go back. Once we get on the plane, we have to go to a D plane, 100% chance. And then we 100% chance have to go to Los Angeles. Right? So those probabilities are 1 and 1, and there's a 0% probability. So P46 equals 0. That means that we cannot possibly transition from the plane onto the train. That would be just like impossible. But the model doesn't know that unless we tell it. So that's what we're doing in this state transition matrix. And now let's talk about the rewards matrix. So this is the reward for each action combined with the current state. So if we start at San Francisco and we choose train, we get an 11-hour reward. In this example, we're actually minimizing reward. So I think Doug Breaker said penalized model. So it is. So actually, we're going to try and minimize our rewards matrix instead of maximizing it. But yeah, the reward from starting from San Francisco and choosing train is 11 hours. And we're going to talk about this forest management example today. So the first time I did this workshop, we were actually in Social Good Week. So that's why I chose this algorithm and this example, because it's a forest management example, and it's really simple. We have a new forest, which is state 0, a middle-aged forest, which is state 1, and a mature forest, which is state 2. Get a flying car. Yeah, get a flying car. That is, I'm going to have to update my Markov decision process model again. Or private jet. Why not? But yeah, so this is the idea here with these. And so in our example, we had a 90% chance that a new forest grew into a middle-aged forest 1 year later. We also had a 10% chance that there was a fire and the middle-aged forest went back into a new forest. And the same with the mature forest. It could grow or there could be a fire and everything would go back to new growth. And in our rewards matrix, we have rewards for cutting down the trees. So if we cut down the trees and they're new, we get $0. In a middle-aged forest, you get some wood from that. And then in the mature forest, you get $2. On the other hand, if you keep the trees and you wait all the way till the mature forest stage, you get a reward from the government. Okay? So now we're going to take a break. It's not a 10-minute break. It's actually a break until the next session. But in the next session, we will implement this model using our Markov decision process. Okay, so I'll see you all for next time. Again, I apologize for the shorter workshop today, but it was great to see you all, and I look forward to seeing you in the next session where we continue this one. All right, take care.